Section: Introduction. In this section, we discuss how we can better utilize confidence metrics to enhance reasoning performance and efficiency. We focus on two main scenarios: offline and online thinking. In offline thinking, we use confidence to improve reasoning by analyzing and combining information from completed reasoning traces. In online thinking, we integrate confidence during the token generation process to boost reasoning performance and/or computational efficiency in real time. We recognize that large language models, LLMs, have shown impressive reasoning abilities, especially when using techniques that improve their performance during testing. One such method is self-consistency, which involves sampling multiple reasoning paths and combining the final answers through majority voting. While this approach, also known as parallel thinking, enhances accuracy, it also significantly increases computational demands. For instance, to raise the accuracy from 68% to 82% on a specific benchmark, we may need to generate over 500 additional reasoning traces per question, leading to a massive increase in token usage. Moreover, we note that the effectiveness of majority voting diminishes as we increase the number of traces, and it often overlooks the quality differences among them. This can result in poor performance if low-quality traces dominate the voting. Recent studies have shown that we can evaluate the quality of reasoning traces using statistics from the model's predictions. Higher confidence in predictions usually means lower uncertainty. By analyzing token-level statistics like entropy and confidence scores, we can filter out low-quality traces to enhance majority voting outcomes. However, we also identify limitations with global confidence measures. They can hide fluctuations in confidence at specific reasoning steps, which are crucial for assessing trace quality. Additionally, these measures require complete reasoning traces to be generated before they can be calculated, which prevents us from stopping low-quality traces early. To address these issues, we introduce Deep Think with Confidence, DeepConf, a straightforward yet effective method that combines parallel thinking with confidence-aware filtering based on local confidence measurements. DeepConf can operate in both offline and online modes, allowing us to identify and discard low-confidence reasoning traces during or after their generation. This method helps reduce unnecessary token generation while maintaining or even improving the accuracy of final answers. We evaluate DeepConf across various reasoning benchmarks and models, demonstrating that it achieves better reasoning performance while generating significantly fewer tokens compared to standard majority voting. In offline mode, DeepConf reaches an impressive accuracy of 99.9% on a benchmark using a specific model, outperforming traditional majority voting methods. In online mode, DeepConf can cut token generation by up to 84.7% while maintaining or exceeding accuracy. We also highlight that recent research has shown we can estimate the quality of reasoning traces using metrics derived from the model's internal token distributions. These metrics help us distinguish between high-quality and erroneous reasoning paths without needing external supervision. We define token entropy as a measure of uncertainty in the model's predictions, where low entropy indicates high certainty. Token confidence is defined as the negative average log probability of the top tokens, with high confidence reflecting greater certainty. To assess entire reasoning traces, we use average trace confidence, which effectively differentiates between correct and incorrect reasoning paths. However, this method has limitations, such as obscuring intermediate failures and requiring complete traces for assessment, which can lead to inefficiencies. In summary, we aim to leverage confidence metrics more effectively to enhance both reasoning performance and efficiency in our approaches. Section Summary. In this section, we introduce Deep Think with Confidence, DeepConf, a method that enhances reasoning accuracy by combining parallel thinking with local confidence-aware filtering to identify and discard low-quality reasoning traces during or after generation. Our approach significantly reduces token generation while maintaining or improving accuracy across various benchmarks, demonstrating superior performance compared to standard majority voting methods. Section: Confidence Measurements. In this section, we address the limitations of global confidence measures, such as self-certainty, by introducing several alternative confidence measurements that focus on the quality of local intermediate steps and provide a more detailed assessment of reasoning processes. We begin with group confidence, which allows us to measure the confidence of intermediate reasoning steps. This method averages the confidence of tokens over overlapping segments of the reasoning trace, creating a smoother and more localized signal. Each token is linked to a group of the previous tokens, and we define group confidence based on the number of tokens in that group. We find that low confidence in intermediate steps can greatly impact the correctness of the final solution. For example, a sudden drop in confidence due to repeated low confidence tokens can disrupt the reasoning flow and lead to errors. Next, we introduce bottom 10% group confidence, which focuses on the mean confidence of the lowest 10% of groups within a trace. This approach effectively highlights the most problematic segments of reasoning across various models and datasets. We also consider lowest group confidence, which looks at the confidence of the least confident group in a trace, further refining our assessment of trace quality. We then propose tail confidence, which evaluates the reliability of the reasoning trace by examining the final portion. We observe that reasoning quality often declines towards the end, making the final steps crucial for accurate conclusions. This metric is particularly important in mathematical reasoning, where strong initial reasoning can still lead to incorrect results if the conclusion is weak. We compare these confidence measurements and find that both bottom 10% and tail confidence are more effective at distinguishing between correct and incorrect traces than mean confidence methods. Moving on to offline thinking with confidence, we explain how to apply these measurements to enhance reasoning performance in offline scenarios. In this context, we generate reasoning traces for each problem and face the challenge of aggregating information from multiple traces to determine the final answer. While advanced methods exist, we focus on standard majority voting. In majority voting, each reasoning trace contributes equally to the final decision. We define the vote count for each candidate answer based on the set of generated traces. In confidence-weighted majority voting, we adjust this approach by weighting each final answer according to the confidence of its associated trace. We calculate the total vote weight for each candidate answer and select the one with the highest weight, favoring answers backed by high confidence traces. Additionally, we implement confidence filtering alongside weighted majority voting to focus on high confidence reasoning traces. This filtering selects the top 10% of traces based on confidence scores, ensuring that only the most reliable paths influence the final answer. We offer two options: the top 10% for scenarios with few reliable traces and the top 90% for a more balanced approach that includes a wider range of traces, reducing bias and considering alternative reasoning paths. Overall, we illustrate how these confidence measurements work in offline thinking and provide algorithmic details for implementation. Section Summary. In this section, we introduce various confidence measurements to enhance the assessment of reasoning traces, including group confidence, bottom 10% group confidence, lowest group confidence, and tail confidence, which help identify low-quality reasoning segments. We also discuss how to apply these metrics in offline settings through confidence-weighted majority voting and confidence filtering to improve the accuracy of final answers by prioritizing high-confidence traces. Section: Online Thinking with Confidence. In this section, we discuss online thinking with confidence. By evaluating confidence during online thinking, we can estimate the quality of generated traces in real time, allowing us to stop unpromising traces quickly. This method is especially useful in situations where resources are limited or quick responses are needed. We can effectively use the lowest group confidence metric in this context. We stop generating traces when the confidence of a token group drops below a certain threshold, ensuring that these traces are likely to be filtered out later. We introduce two algorithms, DeepConf Low and DeepConf High, which use the lowest group confidence to adaptively stop generation and manage trace budgets during online thinking. Our approach consists of two main parts: offline warm-up and adaptive sampling. For the offline warm-up, DeepConf requires a phase to set the stopping threshold for online use. For each new prompt, we generate 5 reasoning traces. The stopping threshold is defined based on the confidence of these warm-up traces, ensuring that we retain the top 10% of the highest confidence traces. DeepConf low uses the 90th percentile, while DeepConf high uses the 10th percentile. In terms of adaptive sampling, we adjust the number of traces generated based on the difficulty of the problem, which we measure by the consensus among the generated traces. If we do not reach consensus, we continue generating traces until we meet a fixed budget. If consensus is reached, we finalize the answer with the existing traces. Since we rely on the lowest group confidence, a large warm-up set helps us accurately estimate the stopping threshold, meaning any trace we stop online will likely be excluded by the offline filter. Next, we describe our experimental setup. We evaluate 5 open-source reasoning large language models, LLMs, from 3 families: DeepSeek-8b, Qwen 3-8b, Qwen 3-32b, GPT-OSS-20b, and GPT-OSS-120b. These models are known for their strong performance in mathematical reasoning and long-chain thinking, and they are fully open source for reproducibility. We test on 5 challenging datasets: AME24, AIME25, BRUMO25, HMMT25, and GPQA. The first 4 are difficult mathematical competition problems, while GPQA includes graduate-level STEM reasoning tasks. These benchmarks are commonly used in evaluations of top reasoning LLMs and are featured in the Math Arena leaderboard. For our baseline, we use self-consistency with majority voting, where each LLM samples 49 independent reasoning paths and selects the final answer based on majority voting. In our experimental settings, we create a common sampling frame by pre-generating a pool of 73 complete reasoning traces. This pool is used for both offline and online evaluations. In offline experiments, we resample a working set from this pool and apply the specified voting method. For online experiments, we also resample a working set to generate traces on the fly with early stopping. We report 4 key methods: single trace accuracy, unweighted majority vote accuracy, confidence-weighted majority vote accuracy, and a method that retains the top 10% of traces by confidence before applying weighted majority voting. We also track the total number of generated tokens, averaging metrics over 77 independent runs. For online evaluation, we implement DeepConf low and DeepConf high using the lowest group confidence with an overlapping window of 78 tokens. Each problem starts with 79 complete traces for offline warm-up, and we set a specific stopping threshold based on the top percentile traces. During generation, we terminate traces whose group confidence falls below the threshold, and we aggregate completed traces using confidence-weighted majority voting, stopping once we reach consensus or the budget. For offline evaluation, we benchmark 3 trace-level confidence definitions and report relevant metrics. Section Summary. In this section, we evaluate the effectiveness of our DeepConf algorithms, which utilize lowest group confidence to dynamically terminate unpromising reasoning traces during online thinking, ensuring efficient resource use. We also describe our experimental setup, including the models tested, benchmarks used, and the metrics for assessing performance, highlighting the importance of adaptive sampling and offline warm-up in achieving accurate real-time confidence estimation. Section: Offline Evaluations. In this section, we present offline results from 3 models evaluated on 5 datasets with a voting size of 75. We compare several methods. PASS@1 measures single trace accuracy. CONS@512 represents unweighted majority voting using 512 traces. MEAN-CON@512 uses confidence-weighted majority voting based on average trace confidence. Bottom 10% CON@512 and tail CON@512 apply confidence-weighted majority voting using the mean of the lowest 10% overlapping group confidences and the mean confidence over the last 2048 tokens, respectively. The 90%, 10% subcolumns indicate the retention ratio in confidence filtering, where we keep the top 11% highest confidence traces before voting. For instance, With a voting size of 75, we retain about 85 traces for voting. Overall, our confidence-aware weighting with filtering consistently outperforms standard majority voting across most scenarios. The filtering with 84% retention shows the most significant improvements, such as DeepSeek-8b achieving accuracy of 82.3% on AMI 25 and Quen 3 to 32b reaching 85.3% on AIME 24. GPT-OS 120b even hits 99.9% on AMI 25. Both local and global confidence measures effectively identify confident traces. However, we note that aggressive filtering can sometimes lead to performance issues due to model overconfidence, as seen with GPT-OS 120b, making conservative filtering a safer choice. We observe substantial improvements over pass at 1 across all methods, highlighting the benefits of ensemble approaches. We also find that using the lowest group confidence effectively captures the least confident token group within each trace. By retaining the top 11% highest confidence traces and applying confidence-weighted majority voting, we achieve consistent gains over majority voting accuracy, with improvements ranging from 0.26 to 9.38 percentage points on various datasets. In the online evaluations, we assess the accuracy-cost trade-offs of our online algorithm by varying the budget, which accounts for all generated tokens, including those from early stop traces. We perform a warm-up with traces to set a stopping threshold using lowest group confidence. We then apply this threshold for filtering after each new trace completes, aligning with the offline version while saving costs from early stop traces. We explore two online variants, DeepConf Low and DeepConf High, which continue sampling until reaching consensus or the budget cap. Compared to the majority voting baseline, DeepConf Low reduces token usage by 43 to 79% while matching or improving accuracy in most cases. The more conservative DeepConf High saves 18 to 59% tokens while maintaining similar accuracy levels. Our results illustrate that DeepConf achieves significant computational savings while preserving competitive accuracy across various reasoning tasks. We find that using the least confident segment to gate traces provides a strong signal for early termination, and the adaptive consensus stop further reduces tokens without sacrificing accuracy. We also include additional analyses and full results in the appendix. Section Summary. In this section, we present offline evaluations of 3 models across 5 datasets, demonstrating that confidence-aware filtering significantly enhances accuracy compared to standard majority voting, with the most aggressive filtering yielding the largest gains. We also introduce an online evaluation method that adapts token generation based on confidence levels, achieving substantial token savings while maintaining competitive accuracy across various tasks. Section: Future Work. In this section, we see several promising directions for future work. First, we can extend DeepConf to reinforcement learning environments, using confidence-based early stopping to enhance policy exploration and improve training efficiency. Second, we need to tackle situations where models show high confidence in incorrect reasoning, which we identified as a significant limitation in our experiments. Additionally, we can investigate more effective techniques for confidence calibration and methods for quantifying uncertainty to better recognize and reduce overconfident but incorrect predictions.